Well, pretty cold. Threw a little bread out to the deer and the chicken, let them eat a little. We're actually, this is what we're going to do here is talk a little about our science type stuff again. Let's see, let me set this thing right here. Talk about the tyranny of time. YouTube has seen fit to give me 15 minutes, but well, we'll go with the 10-minute thing. We'll start with that. Yeah, about 10 minutes. We'll keep watching on that. Okay, what do we got here? A little chilly. When is a good time to sit down? I want to watch the deer here. See what they're doing. Okay, what we're talking about today, of course, is the Big Bang. Big Bang gone bust. And why do I say that? And I hate to sound like the guy who just attacks everything. We're not going to get ahead of this game until we do attack some of these things, and until we do start thinking a little bit more critical than what we've been thinking about. Okay. And why would we say Einstein is wrong? Well, if he was right, we wouldn't be having this discussion. But well, and I'm sure he would have a lot to. He would really like to put in a lot more on this thing, but his time, he didn't get the time to do that. Okay, why is dark matter kind of ridiculous? Why is the Big Bang kind of not there? Well, let's look at what we're doing and why we've gotten to this point. Historical approaches are very, very good. Just don't jump in to the math and the latest gizmo machines and the lights and static electricity, because we need to get a fundamental approach in what we're doing. We need to think, and we're not thinking. A lot of people got jobs and a lot of titles doing nothing, and will nothing come out of it? No, I'm not saying that. And they're really smart people. There's no doubt that they are really smart people. But what we need to do, though, is approach this thing. And I think historical context is a good way to approach it. And another good way to approach it is by getting fundamentally back to the basics. And let's start with the M5 proposition. You know the M5 proposition. We got hydrogen goes in 4, right? And then after hydrogen, the hydrogen number 4, we kind of should go to hydrogen 5 and then, maybe helium. And that's what happened when back in the old, back there in the 30s, when people were looking at light and trying to figure out the universe was made out of mostly hydrogen atoms. Atoms are number 1. And we even now pretty well, I think most people would accept the hydrogen atom is kind of the number 1. It's the first place. It's where it all starts. From hydrogen, once hydrogen is made, it goes right on down to everything else in da-da-dee-dee. Okay. Well, the reason we have this dilemma and the reason we have the Big Bang Theory is because we believe hydrogen is made, in the sun. And that deep in this, with all of this, with this heat and everything, then we make a helium atom. Now, we've tried to make helium, and quite frankly, let me get this knocked down here. And quite frankly, we haven't had much success making elements. I don't, as I recall, no one's made an element yet. Once we do, we'll have this thing down pretty good. But we haven't done that yet. And therefore, we've considered, it's going to take a lot of something, like a Big Bang, an atom bomb. But hey, an atom bomb didn't do it. And of course, an atom bomb wouldn't do it because it falls right into what Galileo saw way back then when he rolled bowling balls up and down. It saw that inverse square event, double the height of your slide there, and you're going to quadruple the length the old bowling ball rolls out, or drop the height of your slide by half, and you quadruply reduce the distance the rolling ball is going to go. And so, inverse square, very important thing. Atom bomb, as it is ignited there, has an inverse square effect. As you go out from the center of the event, you're going to have 4 times less the event. Okay, so radiant energy. Okay, and we have 2 other events here besides inverse square, and inverse square is a biggie. Newton tried to work with it, had a hard time, and everybody else has a hard time with it, but it's one we have to stick with. And the other one is conservation of energy. However this stuff was made, once made, it's going to stay that way for a long time. And we can't do much about it. And we can kind of split a few things and rub a few things like an atom bomb, but we're still not having too much success with that. So, conservation of energy. And the other thing here we're looking at is that we can't see the infinite universe. Right, and we should be able to. Conservation of energy, remember? But we don't see an infinite universe. We see a hell of a big one out there, and we just about can count them all. But there's a lot we don't see. Man, there's some black space up there where there should be no black holes or no black area. So therefore you come up with the, black hole theory. Maybe maybe that's where all this energy went. But we also see other things. We see stars that are forming and getting larger, and we see stars that are dissipating like our own sun. But no matter if it's forming, a star that is forming, or a sun that is dissipating, the other big event we see is conservation of energy. That is, it takes a long time to make something, and it takes just as long to break it down in its parts. That is, it takes forever for a helium atom to form. Hydrogen atom and a helium. But once formed, the hydrogen atom takes a long time to go into helium. And helium takes a long time to go to the next step, and the next step, and that's what we're looking for here. Oh, let's see what the deer are doing. Cut to the chase. Now, dang, they're still eating? Yeah, they're still eating over there. Okay. And it takes a long time. We're doing some patent work here. And it takes a long time to go down. What do we got? 5 minutes? Yeah, about 5 minutes. Okay. And I'm going to write some stuff here to keep our points going for those folks who are interested in this observation. Is that it's kind of chilly. Talk about tyranny of time. Okay, but they've given us a little more tyranny. Okay, so we see this inverse square that's going to have a big event. Conservation of energy. It's going to be another biggie that we can't get around. And the M5 dilemma. And that's what we're trying to explain. And if you look in your history books, for folks who are really getting into this, and I should always do this because I feel that it's one of the finest books written on the subject matter is, can you see this book here? Let's see. See if you get a good one. Yeah, okay, there's his name. M-A-R-C-I-A, Markia, B-A-R-T-A, Bertiski. I don't pronounce his name well, but it's Through a Dark Universe. Very good book, very good historian. Gets it all lined out, so gives you a really good exposure there to it. Recommending books maybe is not the best way to go about it, but that's a good history, and you really need a good history. And maybe some math in there wouldn't be bad. But closing down on our deal. Let's see. With it, don't give a time on this one, does it? Yeah. Let's see. About 8 minutes. We're 8 minutes on the clock right now. Okay. So those elements to understand why the Big Bang doesn't work. Okay. The Big Bang is an idea that it takes a giant amount of energy because of what we see in trying to make a hydrogen into hydrogen 1, 2, 3, and then 4, and then after that we don't go very far with it. Okay, so it must just take a gigantic amount of energy. But how about a gigantic amount of time? I don't like to use the word time, but I prefer distance, because all we really do is measure distance, and I don't care if it's a digital clock or a computer clock. You're still basically what I would call measuring distance. Okay, so for those people who are going to jump all over me for the time thing, sorry, but I really don't. I will use the word time. It's a little easier, but it's a very religious term. Okay, let's call it distance, and let's say that it's going to be a long distance, a number of rotations of the Earth and revolving around the sun to get any of this done. We've been here, our sun has been here for a long time, billions of years, 5 billion, something like, who knows what. And got to go on for another 5 billion or so. What? We're about half-life, everybody likes to say. Looks like we're a lot less than half-life, or a lot more than half-life. But anyway, it's going to go on a long time. Once these atoms finally get to a certain point as they spin up to get to that point. It took them a long time. So conservation of energy, wherever we find them at, they're going to take a long time doing whatever else they're going to be doing. And as once we get this hydrogen atom, whether it be spinning or low spinning or whatever the linear event that's going to go on, and it looks like it's going to go from a very fast spin, but yet we see that hydrogen has very little what we would call inertia. And inertia indicates the amount of spin you have in something. So we could go either way, 2 or 3 ways. One, it has a tremendous amount of spin, or it doesn't have as much spin. But whatever it's doing, whether it has a lot of spin or very little spin, it is now linearly moving through this spin axis. And you could add a little few things to it or less to it or something like that, but whatever. This spin, this event that's going on is going to linearize itself out. And it's going to take a long distance to do that. And there's very little we're going to do to really change it. Because think of the inertia, think of the conservation of energy. But it's something to look into. We're going to look into it. But those are the fields we're looking with. The Big Bang, no, it doesn't work. Dark matter, no. What's there is there. It's not hiding. So let's get used to it. And let's go back to the basics. And that's it. I'm sorry, I'll write a little and have a good evening. It's pretty cold.